So, now in this class we will see how exponential order function affects the Laplace transform. For that one, let us see this one, existence of Laplace transform. That means, whether if I take any function, whether the Laplace transform of that function will exist or not. For that one, we have a theorem which says that if f t is a piecewise continuous in every finite interval and is of exponential order a as t approaches infinity, then Laplace transform of f t, that is f s, exists for all s greater than a. So, you see two conditions basically. If a function f t is piecewise continuous in some finite interval and is of exponential order a, then the Laplace transform of that function exists, and that is f s for all s greater than c. Now, let us see the proof of this theorem. It is given that f t is a piecewise continuous function and in every finite interval and is of exponential order alpha. So, if I assume, if I take a t 0 say greater than equals t, then from the definition of Laplace transform, your f s is 0 to infinity e power minus s t into f t dt. This I can break it into two intervals, 0 to t 0, I am not writing the integrand, and t 0 to infinity, the second part, that is e power minus f t dt. Now, continuity of f t in 0 to, if f t is continuous, say if f t is continuous in 0 to t 0, this implies that this portion 0 to t 0 e power minus s t f t dt, this will exist. Obviously, this integral will exist. So, this will exist for all s greater than a, and also f t is of exponential order a as t approaches infinity. This implies that limit t approaches infinity, e power minus a t into f t, e power minus a t into f t is finite, because f t is also of exponential order alpha. Therefore, this limiting value will be finite and there will exist some real number, I can say m, which must be greater than 0. There must exist some real number m greater than 0, such that this condition should hold from the definition of exponential order function e power minus a t f t. This is less than m for all t greater than t 0, I can say for all greater than t 0, or in other sense your absolute value of f t should be less than m e power a t for all t greater than t 0. Now, what happens? You take this integral t 0 to infinity e power minus s t into f t dt, this you are taking. So, using this inequality, whatever just now we have defined, this is less than equals, we can write down 0 to infinity, sorry, this is not t 0, but this should be t 0 to infinity absolute value of e power minus s t into f t dt. And using this is equals nothing but t 0 to infinity e power minus s t into modulus of f t dt, e power minus s t I can bring outside the modulus. So, e power minus s t into f t dt, and this modulus of f t is less than m e power a t. So, that this is less than equals t 0 to infinity e power minus s t into m e power a t dt. Once I am getting this, so this is again, so using this inequality we are getting t 0 to infinity e power minus s t m e power a t, and this is again you can write down, this is equals, I am just removing this is equals m into t0 to infinity e power minus s minus a into t into dt. And I can find out the value of this integral very easily, that is m into e power minus s minus a into t naught by s minus a, value of this integral. I am not going in details of the integral where s is greater than 0. Now, this m into e power s minus a t naught by s minus a, this I can make as small as possible by choosing t0 sufficiently large. If I choose t0 sufficiently large, then I can make this whole quantity m into e power minus s minus a into t0 by s minus a as small as possible, and hence I can say that this integral t0 to infinity e power minus st into ft dt, this exists, because the value ultimately I am showing that I can make it as small as possible whenever t0 is approaches infinity. Note this one, it can take the value from t0 to infinity. Even if t0 takes the value infinity, then also I will get some smaller finite value. So, dt exists, we can say that this exists for all s greater than a. So, this is the proof of this one, and if I come back to this, just as I told you, f t is a piecewise continuous. I am, for your easy understanding, I am also giving the same thing, t0 is greater than 0. Your fs I can write down Laplace transform of ft e power minus st ft dt. This I am dividing into two parts, 0 to t naught and t naught to infinity, and since continuity of the function in the finite interval, always 0 to t naught e power minus st ft dt will exist, and we have to show that t0 to infinity e power minus st ft dt will also exist. And we know f t is of exponential order a as t approaches infinity. From there, we know that limit t approaches infinity, e power minus a t f t dt is finite, or in other sense, absolute value of e power minus a t f t is less than m, and this I can write down absolute value of f t less than m e power a t. Using this, now I have the integral of absolute value of t naught to infinity e power minus st f t dt, which is less than equals t naught to infinity absolute value of e power minus st f t dt, and this is equals, again modulus can come only on f t e power st, I can bring it outside, so that I can write down t naught to infinity e power minus st f t dt, and this is less than equals using the earlier inequality t0 to infinity e power minus st into m e power a t, because modulus of f t is less than equals m into e power a t, and I can find out now the value of this integral as this m into this one. And then, as I told you earlier, this value m into e power minus s minus a into t naught by s minus a can be made as small as we please by choosing t naught sufficiently large, which means that t naught to infinity e power st f t dt, this integral always will exist for all s greater than a. So, this completes the proof. Please note this one. This completes the proof that the Laplace transform of a function will exist if the function is a piecewise continuous function and it is of exponential order alpha. Just a general definition, a function of class a function which is piecewise continuous on every finite interval in the range t greater than 0 and is of exponential order as t approaches infinity, is known as function of class A. Or in simple way, I can say that if a function is of class A, that means that the function is of exponential order function. this we can take directly that the function is of exponential order alpha. And if f t is of class A, then Laplace transform of f t exists, because for all a's greater than a, the reason is that your function is of exponential order. Now, alternative proof of existence of Laplace transform. We gave the one proof, I am just giving the another alternative proof. I can start from here. Modulus of f s equals modulus of 0 to infinity e power minus s t f t dt, and this is less than equals again 0 to infinity e power minus s t modulus of f t dt. Directly I can write down, which is less than equals m 0 to infinity e power minus s t into e power a t dt. This is actually similar what we did in the earlier case, m into 0 to infinity e power minus s minus a into t dt, and I can find out the value of this. This is equals m by s minus a, because the integral value whatever I will obtain, the finite value is m by s minus a for s greater than a. Therefore, f s converges absolutely we can say, and hence converges. Since f x converges absolutely, hence converges, therefore, your f s exists. There is a remark on this. Please note this one. The condition given in the theorem for existence of Laplace transform are sufficient for the existence of Laplace transform. Please note that it is a sufficient, but the not necessary. Means it is not that if and only if, it is only a sufficient condition, not necessary condition. It means that if these conditions are satisfied, Laplace transform of that function must exist. But if these conditions are not satisfied, Laplace transform of that function may exist, may not exist. Please note this one. This is a sufficient condition. Sufficient condition means if the conditions are satisfied, Laplace transform of the function will exist or must exist. But if the conditions are not satisfied, then Laplace transform may or may not exist. Let us take one counter example of this. You see this function f t equals 1 by root pi t, which is infinity at t equals 0. From the function itself it is clear, at t equals 0 the function does not exist, but you will see that its transform always exists. What is the Laplace transform of 1 by root pi t? From the definition, it is 0 to infinity e power minus s t into 1 by root pi t dt, that is the normal case. So, once I am writing this, this is equals 1 by root pi, I am putting the value 1 by root pi I am bringing outside, 0 to infinity e power minus s t into t power minus half, and this is on this if I put s t equals x, then the problem will be transformed to 1 by root pi x, 0 to infinity e power minus x into x to the power minus 1 by 2 dx. This I can write it in terms of gamma function directly, because here it is 1 by root pi s into gamma half, and this is gamma half is nothing but 1 root pi. So, that the value of the Laplace transform of the function 1 by root pi t is equals 1 by root pi s. So, please note this one, that whenever I have a function like this f t equals 1 by root pi t, this is neither piecewise continuous nor of exponential order alpha, since at t equals 0 value of the function is infinity. Still we have shown that the Laplace transform exists. Therefore, please note that the conditions what we have given for existence of Laplace transform, that is a sufficient condition, means that if the Laplace transform exists, in that case if the function is satisfying the condition, Laplace transform will always exist. but if the function is not satisfying the condition, Laplace transform may exist, may not exist, we cannot conclude. Now, let us try to find out the Laplace transform of some functions. Let us see the function f t equals t to the power a. This is a is having greater than minus 1 say. From the definition, Laplace transform of t to the power a, this is equals 0 to infinity e power minus s t into t power a dt. If I put s t equals x, if I put say s t equals x, this I can write down 1 by s to the power a plus 1 0 to infinity e power minus x into x to the power a dx. This x to the power a basically now you can write down e power minus x into x to the power a. This you can write down a plus 1 into minus 1 also. So, that I can write it in terms of gamma function, and which is equals to gamma a plus 1, because x to the power n minus 1, n is a plus 1. So, that it is gamma a plus 1 by s to the power a plus 1, where s is greater than 0. So, Laplace transform of t to the power a is greater than minus 1, then the Laplace transform of t to the power a will be gamma a plus 1 by s to the power a plus 1. And using this, if I take that f t equals t power n, where n is positive integer. We have done it t power a, when now we are assuming f t equals t power n, where n is positive integer. I can tell that Laplace transform of t power n, this is equals gamma n plus 1 by s to the power n plus 1, and gamma n plus 1, as you know, this we can define as factorial n by s to the power n plus 1, where obviously s is greater than 0. So, if I have a function f t equals t power n, where n is positive integer, please note that Laplace transform of t power n is factorial n by s to the power n plus 1. Now, you can consider n equals 0, 1, 2 like this way, and you can get various transform. So, from here when n is 0, then Laplace transform of 1 will be equals to n is 0, 1 by s. Laplace transform of t, Laplace transform of t, from here n is 1, so 1 by s square. Laplace transform of t square, if I find out t square, which is equals to factorial 2 by s to the power 3, like this way I can find out the Laplace transform of various functions. So, you have to note the Laplace transform of some useful functions. One is t to the power n, where n is positive integer, that is equals factorial n by s to the power n plus 1. Now, let us again go back to the screen. So, this thing again just I am showing whatever I did it in pen. Laplace transform of t to the power a is this one, it will be easy for you to understand, and this is nothing but gamma a plus 1 by s to the power a plus 1, and therefore, Laplace transform of t power n when n is positive integer is factorial n by s to the power n plus 1. Now, the next is find the Laplace transform of the function f t equals e power a t. So, your function is e power a t, we want to find out the Laplace transform of this function. Laplace transform of e power a t equals 0 to infinity e power minus s t into e power a t dt. This equals, you can write down 0 to infinity e power minus, if I combine it, s minus a into t into dt. And if I evaluate the integral, it will be minus e power s minus a into t by s minus a, where t lies from 0 to infinity. And if I calculate the value, if I put the infinity, one part will be 0, other part will be 1 by s minus a, where s is greater than a. Therefore, please note that whenever I want to find out the Laplace transform of e power a t, this is equals, I can find it like this way, 0 to infinity e power minus s t e power a t dt, and by this process ultimately I am obtaining the Laplace transform of e power a t as 1 by s minus a. Now, let us see the next one. So, just I am showing this thing again, so that you can understand in the better way. 1 by s minus a is the Laplace transform of e power a t. Now, let us see the Laplace transform of the function sin a t. As I have told you, Laplace transform of sin a t is equals to 0 to infinity e power minus infinity into 0 to infinity e power minus s t sin a t dt. And if I use the integration by parts, I will obtain e power minus s t by a into cos a t, t lies between 0 to infinity, minus s minus a into 0 to infinity e power minus s t cos a t dt. And if I evaluate this, again I can write it like this way by putting the values, and if I ultimately get it, this becomes that the first part is this minus s square minus a square by Laplace transform of sin a t. This left hand side, Laplace transform of this one s square minus a square by Laplace transform of sin a t, I can bring it on the left hand side, and if I bring it, then 1 plus s square by a square into Laplace transform of sin a t, this is equals, this limit I have to find out, and if I evaluate, I will obtain the next step like this, and therefore, I am getting Laplace transform of sin a t equals e power minus s t by s square plus a square into a cos a t plus s sin a t, t equals 0 to infinity. And so, I can obtain this one. From here, if I evaluate, I will obtain as t approaches infinity. Here, if you see the earlier one, a cos a t plus sin a t is there. This one, a cos a t plus s sin a t by s square plus a square is bounded. Therefore, this goes to 0, this integral, and as t approaches 0, e power minus s t approaches 1, and a cos a t plus s sin a t by s square plus s square approaches a by s square plus s square. So, and this one is approaching this thing. Therefore, from here I can tell that Laplace transform of sin a t, this equals a by s square plus s square. So, if I see now find the Laplace transform of the function cos a t, just like earlier one. Let us do it. Laplace transform of cos a t, this is equals 0 to infinity e power minus s t into cos a t dt, and this equals, directly I am writing, I am not writing all the steps. You will get e power minus s t by s square plus s square into a sin a t minus s cos a t, and t varies from 0 to infinity. If I evaluate the integral, I will obtain, you see, s by s square plus s square, where s is greater than 0. So, please note this thing, that Laplace transform of cos a t is s by a s square plus s square, but the Laplace transform of sin a t is a by s square plus a square. So, please note this thing, I can evaluate these things by this thing. Now, we have proved one thing, if you see, that is mod of f s is always less than equals m by s minus a when s is greater than a. Therefore, whenever limit s approaches infinity, since absolute value of the Laplace transform of a function less than equals m by s minus a. So, if I write down as s approaches infinity, this value should be equals to 0, because this is m by s minus a. So, you are getting Laplace transform of s approaches infinity f s, this is equals to 0. So, absolute value of s f s, this is again s m by s minus a, and this I can write down m by dividing by s on both sides, this is equals to 1 minus a by s, and this is I can write again less than equals m if your m is large enough. Please note that modulus of mod of s f s is less than equals s m by s minus a, which is equals m by 1 minus a by s, which is less than equals m when m is sufficiently large. From here, can we conclude one thing, that there are functions like 1 s or s by s minus 1. This type of function can, you see, 1 s by s minus 1, this type of function can never be Laplace transform of any function, because as s approaches 0, these functions will never approach 0. This we have shown here, that as s approaches infinity, your f s should be equals to 0. Please note this thing. Since s approaches 0, f s equals 0, s approaches infinity, f s equals 0. Therefore, the functions like 1 s, s by s minus 1, this type of functions can never be a Laplace transform of any function. You consider the unit step function. Unit step function we defined various ways, u t naught of t, sometimes we say it as u t minus t naught. This is equals to 1 for t greater than equals t naught. This is equals 0 whenever t less than t naught. And this is not a continuous function, this is piecewise continuous. This is 1 for t greater than equals 0 and 0 for t less than 0. If I try to find out the Laplace transform of u of t minus t naught, Laplace transform of u of t minus t naught will be 0 to infinity e power minus s t into u t minus t naught dt. So, u t minus t naught means I have to break it into two parts, one will be 0 to t 0, other part will be t 0 to infinity. Now, in 0 to t 0, this part will be 0, because in 0 to t 0 the value of the function is 0, and here the component will come as 1, that is e power minus s t into 1, because u t minus t naught is 1 dt. And if I evaluate this integral, I will obtain as minus of e power minus s t by s t naught to infinity. And if I evaluate the limits, then I will obtain e power minus s t naught by s, where s is greater than 0. So, please note that Laplace transform of this step function is e power minus s t naught divided by s. And if I go back here, just we have done cos a t, that is fine. Now, find the Laplace transform of cos hyperbolic a t and sin hyperbolic a t. The Laplace transform, if I take cos hyperbolic a t cos hyperbolic a t, we know this is nothing but e power a t plus e power minus a t divided by 2. So, it is basically half into Laplace transform of e power a t plus half into Laplace transform of e power minus a t. And I know already Laplace transform of e power a t is 1 by s minus a, already we have done it. So, plus half into 1 by s plus a. So, if I combine them, this will become s by s square minus s square, where s is greater than absolute value of a. So, therefore, Laplace transform of cos hyperbolic a t is equals to s by a s square minus s square, and on the same fashion you can do it like this. Laplace transform of sin hyperbolic a t will be equals to a by s square minus s square, where s is s, where your s is greater than absolute value of a. So, please note that Laplace transform of cos hyperbolic a t is s square s by s square minus s square, and Laplace transform of sin hyperbolic a t equals to a by s square minus s square. Thank you.